Right, this video here is all about stellar parallax. Now, stellar parallax is a way that we can actually measure the distance to sort of fairly nearby stars. Now, what I'd like you to do is basically pick a point somewhere in your room, perhaps well away from your computer, somewhere quite a way away. And what I'd like you to do is put your thumb out in front of you, do a cheesy kind of thumbs up. What I'd like you to do then is basically look at the image by closing your left eye. And what you should see is that the thumb appears to be in one position. If you then close your right eye and open your left eye, the thumb moves position, or it appears to move position. But things which are far away tend to stay in the same place in your view. And this is very similar in many ways to stellar parallax. Basically, when we look at objects which are kind of quite close to us, they appear to change position, but things a long way away appear to be in one position. And this was noticed with stars. What they found was that when they looked at the galaxy around us in the solar system, the stars outside of our solar system, when they took a picture in the summer, they might find that you have this kind of arrangement of stars. But in the winter, one star would appear to change position, and then the next summer it would be back in the same position. Now, it's not that the star is moving from one place within our galaxy to another, but it's due to the fact that this star is closer than the really, really distant stars. And this is a way that we can actually work out the distance to fairly close by stars within our galaxy. Okay, so with stellar parallax, what we have is the sun in the middle here. We've got the Earth at one position and then at another position, perhaps another 6 months apart. Now, these things here are just going to be my stars, which are a really, really long way away. And basically what we have is this blue star, which is the one that appears to change position as the year goes on. Now, if you look at the blue star, when the Earth is in this position, I'm just going to draw a line over to that. What you tend to find is that when you look at this star, you see just to the left of it, you have an orange star, then you have the blue star, then you have a yellow, a red, and a yellow. And basically what we just see is this kind of, just kind of a 2D image of where it is. If, however, the Earth changes position, which it does every 6 months, when you look at that same star, this star now appears to be in a different position relative to the stars which are quite far away behind it. So if you were to be looking in this direction, you now see an orange star, a yellow star, and a yellow star just to the left of the blue star, and then you see the red and the yellow to the right. And basically what we have is this apparent change in position. Now, what do we know about this diagram? We can add kind of a couple more lines to it. First of all, we have the baseline here. And this is a bit like your eyes, and that's your nose in the middle, when we looked at your thumb kind of held up against things behind it. And we know that the distance between the Earth and the Sun is equal to 1 astronomical unit. The other thing is that we're really trying to find out effectively the distance between the Sun and this star here. And what we can actually do is by looking at photos, we can actually measure the angle here, theta. We can measure this angle, and if we know that angle there, we know this is 1 astronomical unit, we can then work out this distance over here. And effectively, I could call it theta, or I'm going to call it p, okay? Where p is what we call the parallax angle. And you might remember from a lot of the practical work that you do that the parallax error is when you're kind of measuring something, and if you don't look at it head on, it tends to be in a slightly different position. Now, if we measure the angle p in arc seconds, there's actually quite a nice relationship. And this is due to things like tan theta equals theta for a small angle. And what we find is that the distance is equal to 1 over p. And basically what this means is if you measure p in arc seconds rather than converting it to degrees, this then gives our distance in parsecs. And what you might find is that as p gets smaller and smaller, it's going to be harder to actually work out the distance, because it gets to a point where it's really hard, bearing in mind a lot of this stuff happened a long time ago using sort of fairly old style telescopes. As p got smaller and smaller, it gets harder to actually measure it very precisely. And what we find is that we can get values of p to about, a hundredth of an arc second, and therefore this limits our distance to be approximately equal to 100 parsecs, which is about 300 light years. So, looking at stellar parallax, stellar just means to do with stars. Parallax is due to the difference in the apparent position due to the angle. And basically what we know is that if we look at the same star at different times in the year, relatively close stars appear to change their position relative to the background. If we know that the distance between the Earth and the Sun is 1 astronomical unit, and the angle P here is measured in arc seconds, the distance to the stars in parsecs is equal to 1 over that angle in parsecs. And this only works to stars which are about 100 parsecs away from the Earth. Away from that, stars which are really distant, they're so far away that actually they don't tend to change their position at all. So I hope that makes sense, and leave any comments in the video below. Thank you very much.